Okay, so today we are looking at section 6.2, so if you want to follow along in your book, you can. But we're talking about two topics, the first of which is something called enthalpy, and the second of which is something called calorimetry. Okay, and both of these things deal with measuring heat. Okay, so enthalpy right here, this word right here, enthalpy, is given by this H. Okay, and most of the time it's given by delta H. What does delta H stand for? What does delta mean? Change in, right? The change, and it usually means final minus initial. Okay, delta means change in. So enthalpy is really a measure of a reaction or of a system's total heat and total energy, right? We've talked about heat specifically, the variable Q, and we've talked about work, but now this puts all of those things together. Okay, so the enthalpy is basically the total measure of energy or heat within a system. Okay, when we get down here, we're going to start looking at this delta H value a lot. Okay, the enthalpy of the products minus the enthalpy of the reactions, which is essentially final minus initial. And then these are two things. You can put those on that big cheat sheet if you want for enthalpy values. If it's positive enthalpy, that means we've got an endothermic reaction. And if it's negative enthalpy, we've got an exothermic reaction. Tell you the delta H value for the reaction. Okay, so get this written down, and then we are going to start working through a problem here to calculate our enthalpy change. Okay? Calculator and periodic table, so when you get done with writing down what you need, you will need to have that out. All right, so let's take a look at this delta H value given. Negative 2,221 kilojoules of energy. Is it energy that's flowing in or energy that's released? Energy is released because it's negative, right? Our delta H value is negative, which means heat's flowing out of the system. So for every 1 mole of propane that's burned, because in the chemical reaction, right, we have 1 mole of propane. So this delta H value that is given is for this particular reaction, meaning for this amount of substance. 1 mole of propane, 5 moles of oxygen, 3 moles of carbon dioxide, 4 moles of water. For this particular reaction, at this ratio, this is how much heat is released. Okay? So if we had doubled the reaction, if we started with 2 moles of this, and 10 moles, and 6 moles, and 8 moles, then we would have double the amount of energy released. Does that part make sense? That delta H value is proportional to the amount of substance that goes in. Okay, does that kind of make sense? Yes or no? Okay, because this reaction is balanced the way it is, that means that 2,000 roughly, okay, negative 2,000 kilojoules are released. Okay? So if we were to adjust the amount of propane that we're burning, that means our heat released will alter also. Okay, so we're going to do that. We're going to say, assume all of our heat comes from the combustion of propane, so that's nothing extra is happening. We're not doing work. We're not having anything else extra happening. We're going to calculate our delta H if we only burn 5 grams of propane, not 1 mole of propane, right? We're only going to burn 5 grams instead of 1 mole of it. So do we expect our delta H value to be greater than or less than 2,221 kilojoules released? Less than, right? 5 grams is less than 1 mole of that propane. So we're going to calculate that, okay? So we're going to see, first of all, if we know that this is how much is released for 1 mole, we need to find out how many moles of propane are we actually using, right? How many moles of propane is 5 grams? So we're going to find that first. Okay, so I'm going to do it kind of up here at the top so I have some room. Okay, if I have 5 grams of C3H8, I want to find out how many moles of propane is that. Okay, so I need to convert from grams to moles of propane. Okay, what does moles always get? The 1. And what value goes with grams? Yeah, the molar mass of this, which in this case is 36 plus 8, 44. Okay, so I'm going to take 5 divided by 44, and I know that I'm working with 0.1136 moles of C3H8. Are we on the same page so far? So if I were going to reduce all those coefficients down to match this, right, I would have a fraction of the heat release. So we don't have to do that. We don't care how much oxygen's going in or anything like that because it says we're dealing with excess oxygen. So if I know I started with this many moles and I know this much heat is released per 1 mole, what can I do to find out how much heat is released? Not subtract, I can multiply. Okay, so I'll show you how this works out. Okay, if I know that, I'm trying to find room here. Can I erase the reaction? Are we okay with it? Okay, if I know that that much heat is released, negative 2,221 kilojoules happens per 1 mole, right? This value would be whatever the coefficient is in the problem, right? But in this chemical reaction, it was a 1 coefficient. So this much kilojoules is released per 1 mole of C3H8, and I know I have 0.1136 moles of C3H8. So that cancels that and leaves me in kilojoules, which is what I want. Okay, so you're just multiplying them together, but I'm showing you how the units match up with that. Okay, so I'm going to take negative 2,221 times 0.1136. And I get negative 252.3 kilojoules released. This would be if we were using 5 grams or 0.1136. So this is just the amount of heat that's released. It's just the kilojoules. So it would be per 0.1136 mole, but you don't have to put that in there. Okay, I just put the for 1 mole of propane so we could see that it related directly to the reaction. Okay. If there was a different coefficient on propane, you would have to say like per 2 moles or per 3 moles if there was a different coefficient there. But since it was a 1, then we just keep it.
So those propane moles we multiply on top of right over.
Exactly.
So the whole reaction was propane?
The whole reaction was propane burning and oxygen. Yeah, so propane was hot, and then it will make carbon dioxide and water. Yeah. Okay, any other questions? Okay. All right. When 1 mole of CH4 is burned at constant pressure, 890 kilojoules is released. Calculate the delta H for a process in which 5.8 grams of methane is burned. So this time we're doing it without the reaction, but it tells us that for 1 mole of methane, we know how much energy is released. We could write out a balanced chemical reaction here, but we don't have to. There's not really a need to do that because we know that for 1 mole of CH4, we release this much energy. Okay? So delta H of the reaction, is it positive 890 or negative 890? Why positive? If it's released, that means it is negative. Right, so that's something that you guys, hopefully you picked up on that on your homework last night. There was several places where your work needed to become negative. You just have to know that based on if it's doing work on the system or by the system, things like that. So you need to pay attention to if it's bringing in heat, we'd have a positive H value. If it's giving off heat, we have a negative H value. So negative 890 kilojoules, okay? But that's for 1 mole of methane. We're not using 1 mole of methane here. We're only using 5.8 grams. So what's our first step here? Convert to moles. We want to find out how many moles of methane do we have. Okay, so I go grams of CH4 to moles of CH4. If you really wanted to do this in one step, you could. Right? I could keep going. I could say 1 mole of CH4 is negative 890 kilojoules of enthalpy. Right? I could keep going in that T-chart. If that makes more sense to you, then do it. If it doesn't, then just stop at moles. Okay? And then do the multiplication elsewhere. But okay? I've canceled grams. I've canceled moles. I'm left with kilojoules, which is what I want. So I multiply across the whole top, divide by the whole bottom.
And this is defined.
This is delta H right here. So this would be delta H of the whole reaction. This is delta H if we just use 5.8 grams. Right, so it's just a smaller amount of heat that's released. Or enthalpy. Okay, I should say enthalpy, not heat.
Negative.
So up here, this negative comes from the fact that it was released as heat. So if it said heat flowed in or it brought in heat or whatever, then it would be a positive 890. Okay. Any other questions about how I got that? Or how we calculated that? You could do it in one step T-chart like this, or you could stop at moles and say, I know I have X number of moles, and if I know it's this many kilojoules per mole, I can multiply that out. Okay, any other questions? Yeah.
So what if it was more than 1 mole?
You would put that mole right here. If it was 890 kilojoules per 3 moles, you'd put that there. Okay? Okay. All right, the next part of section 6.2 is dealing with something called calorimetry. And calorimetry is how you measure heat in a chemical reaction. So we've talked about the amounts of heat in chemical reaction, but now calorimetry is how you measure it. Okay, you use something called a calorimeter. Okay? So go ahead and get written down what you need on here, and then I'll talk through a couple things that we're going to look at. Okay, so with calorimetry, there are two different types of what we call heat capacities. And the most common one and the one we will use most often is the one called specific heat capacity. And that's what it takes to raise 1 gram of substance by 1 degree Celsius. It's the amount of energy required to make 1 gram of a substance increase in temperature by 1 degree. Okay? The molar heat capacity is the energy required to raise 1 mole of substance by a degree Celsius, and sometimes you'll see Kelvin instead of Celsius, but the increase rate between Kelvin and Celsius is the same because it's a 1-to-1 ratio. So 0 Celsius is 273 Kelvin, okay? And 1 Celsius is 274 Kelvin. And 2 Celsius is 275 Kelvin. So the change in temperatures between Celsius and Kelvin, the change value is the same for those. Does that kind of make sense? They have the same. Whereas 0 degrees Celsius is 32 degrees Fahrenheit. But 1 degree Celsius is like, maybe 35 degrees Fahrenheit or whatever. I don't know the conversion. That's like 9/5 or something silly. But that's not a 1-to-1 change. Does that make sense? So Celsius and Kelvin have the same change rate. They just have a different starting point. So on molar heat capacity, sometimes you'll see Kelvin in there instead of Celsius. It doesn't change it when we use delta. That's always the changing. Okay, so specific heat capacity is what we're going to use a lot. Specific heat capacity is an assigned value for every different type of substance. So water has a specific heat. So it says it takes this much energy per 1 gram of substance to raise it 1 degree Celsius. And every individual element has its own specific heat capacity. It has its own value. It's like a constant. And there's tables and tables and tables of specific heat capacities. There's specific heats for types of reactions. There's all these types of things. But we are going to be able to calculate the amount of heat that it takes to raise 10 degrees or whatever. It depends on its mass and the amount of heat that's going in and how much temperature change there is. So we have an equation for that, okay, which I'm going to give to you now, okay? So this is what we call the specific heat capacity equation, okay, for calorimetry. Q equals ms delta T. This is big, big, big. You want this on your equation sheet or on that cheat sheet I gave you, but this is big, okay? M has to be in grams, that's the mass. S is the specific heat, so that's going to be a constant that you're given from a table or from a book or something. That's usually going to be given to you. And then what's delta mean? The difference or change in temperature. So you have got to remember that it's final minus initial. Okay, final minus initial. Because in problems it will say the temperature went from 10 degrees to 20 degrees, and so you'll want to plug in 10 minus 20, right? But it's 20 degrees final minus 10 degrees initial. You need to pay attention to that. Okay, this is for specific heat capacity. So you might want to make a little arrow in your notes or whatever. This is specific heat capacity. I'm going to give you a different equation for molar heat capacity. We will use this one by far more often. Okay, so
this one is specific?
this is specific heat capacity. I'm going to give you a different equation for molar heat capacity. Sorry, do you need me to go back?
No, I was just curious. How do you know the difference between specific and molar?
So this is molar heat capacity, and it has a little bit of a different equation. Q equals NC delta T. So N is the number of moles of our substance, not the mass of our substance. Number of moles of substance. C is the molar heat capacity. I forgot to change that word. This is molar heat capacity. Sorry. And then T is still the change in temperature, but in Kelvin this time instead of Celsius. So you know the difference based on their equation, and the value for the constant is C instead of S. So this is molar heat capacity. Everyday chemistry way to do calorimetry. And so they put 2 styrofoam cups, and they're going to measure the temperature of the solution. What are the styrofoam cups for? Why styrofoam instead of like glass? They insulate it. So they keep the heat in, which means it gives us an accurate read. And so this is what a calorimeter kind of looks like. It's a closed container, right? It's got a lid on it that just has a thermometer and then a stirrer in it. That's it. So it's a closed container, and we can make them really simply. So coffee cup calorimeters are really kind of common, even in a little bit higher level chemistry, because they generally do the job with pretty low tech things, right? So this is an example of coffee cup calorimeter, and we'll do a reaction when we use one of these, but it's just a closed surface. It's got 2 styrofoam cups, one to hold the reaction and one as an extra insulator, and then it's got a lid, and then your thermometer reads the temperature that happens in the reaction. And that's it. Okay. So here we go. Let's try some practice with calorimetry. Okay. How much energy or heat is required to change the temperature of water by 415 degrees? So if we're looking for heat, remember that's Q. And our value was given to us in grams. So we want to use MS delta T.
And so if it's given to you in grams, you should use delta MST, or you should use MS delta T. But if it's given in moles, you should use yellow.
Correct. Unless it specifically would ask you for molar heat capacity, we're going to use this one almost all the time.
If it's in grams.
Yes. Okay, so right now, we know that our mass is 50. We know our delta T is 15. We're solving for Q, but we don't know our S value either. Right? What did I say about S values? Where do they usually come from? A chart or a table. So on page 254 in your textbook is a table of really common specific heat values. If you don't have your book, that's okay. I'll give you the value. I just want you to see where there are some listed. There's a much, much bigger tables, probably in the back of your book too, but okay, table 6.1 has some specific heat capacities. So what do we think? What do you think the one that we need is? Water. And do you see the 2 differences in the water values? One is for solid and one is for liquid. So which one do we need? Liquid. Okay, so the S value is 4.18. Do you see the units on specific heat capacities in the specific heat capacity chart? Joules per degrees Celsius grams. Okay, I don't really care that you know the units necessarily, but you need to understand that in order for this value to work, we have to have our temperature measured in degrees Celsius, we have to have our M value measured in grams, and our Q value will come out in joules, not kilojoules. Okay, so you need to just pay attention to what those units are, that they all kind of like jive together. Okay, this is a number that we'll use a lot. We'll see a lot of reactions with water, so 4.18 will become pretty common for you, but just FYI. Okay, so we say Q equals M S delta T. This time they gave us the temperature change. They didn't tell us what it goes from or to and from, but it tells us the temperature change was 15. So we just plug it in. 15 times 4.18 times 50. So Q equals 3,135 joules. Right? And it didn't tell us necessarily that it heated 15 degrees or it cooled 15 degrees. It just told us it changed 15 degrees. But since it's left as a positive 15, we're assuming that it's heating up, which means our heat is being added. So our Q value is positive. right? You don't have to include that, but it might tell you it's cooled by 15 degrees, in which case you'd have to add that negative, right? Yeah. Okay, great. Okay.
You have to put the negative in front of it.
You would put the negative with a 15. So just make sure you're looking for context clues in those questions. Heated means heat goes in. Cooled means heat goes out. Okay, questions about that?
So the delta doesn't do anything in the comments?
So when it says it changed 15 degrees, we don't have to do anything. But if it said it goes from 10 degrees to 25 degrees, then we would go 50 times 4.18 times 25 minus 10, and that would give us 15. You know what I'm saying? Okay. All right, what's the final temperature after 840 joules is absorbed by 10 grams of water at 25 degrees Celsius? What does absorbed mean? Coming in or going out? Coming in. So we keep it positive 840. What's our S value here? Still 4.18 because it's still liquid water. Right, I like to list out all of my variables. So I know that my initial temperature, that's what I just make TI, that means temperature initial, right? My initial or my starting temperature is 25. My final temperature is what I'm solving for, which is why I put my question mark there. Okay? So I like to list all my variables kind of in the margins if I have a chance to do that. Then I can use my specific heat, so Q equals MS delta T. So I know my Q is 840. My mass is 10, 4.18. Now we have to put in our temperature final minus 25. Okay. Algebraically, what can we, do you know how we can solve for TF? Any ideas? Remember, these are all multiplication terms through here. Okay, so I can distribute all of these through, or I could just divide over 10, divide over 4.18. Right? I can multiply those together and then divide them over. Because I want to get this term by itself. Right? Because it's got my TF in it. Does it? Okay, hold on. I'll stop. Okay. Does it make more sense for you guys to just distribute the 10 and the 4.18 through the whole thing? Okay, we'll just do that. That's fine. So 10 times 4.18 gives us 41.8 TF. Minus 10 times 4.18 times negative 25 equals 840. Okay, so do we see what happened there? Yeah, you may. I distributed these through to my TF, and then I distributed these through to my negative 25, and I got there. Does that make sense? If you are not getting the algebra, that's okay, but you just got to tell me because I don't know. Okay, from there, what can I do? Add over my 1045, right? I'm going to combine my like terms. I get positive 1885 equals 41.8 TF. And then what can I do? I divide over my 41.8. Oops. and we get TF equal to 45.1 degrees Celsius. If the first temperature is given in Celsius, then our final temperature is Celsius. If the first one's Kelvin, then the final will be Kelvin. Okay? Any questions on the algebra as to how we got through that? Okay, great. Now we're going to try when we put two things together. And we're going to look at the specific heat of it. When we mix two things. Okay, so get this written down and then we will work through it together. Oh, not yet, not yet. That's one more problem away. Still write this down. We're not mixing two things just yet, like I was talking about. Never mind. M, which is both of our masses added together, right? 12 grams plus 50 grams, times the specific heat of the solution, 3.9, times delta T, which we said was 29 minus 25. So you can plug that in.
So you don't want us to actually subtract?
Yeah, you can go ahead and just plug in a 4 there if you want. That's fine. I just usually don't take the time to do that ahead of time. I just kind of do it all in one thing. But that's totally up to you. So 62 times 3.9 times 4. It gives us 967.2 joules. And should it be positive or negative? Positive, right? Because we're heating up. A 100-gram sample of water at 90 degrees is added to 500 grams of water at 10 degrees. Calculate the final temperature of the water. A 100-gram sample at 90 is added to 500 grams at 10. Calculate the final temperature of the water.
So
This is its specific heat. But we have to look at this a little bit different, okay? So we have two samples. They both happen to be water, but we have two samples, okay? First one and our second one. Okay, so what we need to think about this is that these two things are going to come to what we call an equilibrium. They're going to reach a central temperature. Agreed? Right? We're going to pour in 90 with 10 degrees. Eventually, they're going to reach a temperature somewhere in the middle. Right? Would you agree with that?
Yeah.
So that's what we're looking for. But the way we do that is we set our two Q values equal to each other. Right? And so we spread that out where we can expand that to say MS delta T equals MS delta T. Right? This is for our first substance. And this is for our second substance. Okay? So, for our first sample of water, we had 100 grams. What's the specific heat of water? 4.18. We don't know our temperature final, but we do know our initial temperature, and it was 90. Right? The first sample poured in at 90 degrees. Okay? Second sample is 500 grams. Still the same specific heat. We don't know temperature final, but we do know temperature initial was 10.
So why do you put them equal to each other?
So you put them equal to each other because this thing is going to become some equilibrium. They're going to have the same final temperature. So we have to, since they're both, well, yeah, since they interact and they're in one container, they're going to reach the same final temperature. So we act like the energy lost from one is equal to the energy gained of another. So one of these has to be losing energy. Which one of them is going to be losing energy, do you think? The first one has to be losing energy because it's going from 90 degrees, and we said the temperature was going to fall somewhere in between 90 and 10, right? So if that one's losing energy, you have to tack on a negative to that. Basically saying the energy lost by this one is equal to the energy gained by this one. That's why we set them equal to each other. Okay? So it's not always that the first substance gets a negative or the second. That's not the case, right? You have to just pay attention to which substance is cooling down. That one gets the negative. Okay, does that make sense? Okay, so now that we're here, we need to start doing some algebra to get TF both on the same side, right? So I'm going to go ahead and distribute through like we did in our last problem. If you can solve the algebra quicker, that's fine, go for it, right? But I'm going to show you how we get there. So I'm going to distribute this all through, right? The 100 times 4.18 times TF, then I'll go 100 times 4.18 times negative 90. Do we see the algebra that happened here? Right? I multiplied these two together and I got that times TF. And then since these were both negatives, right, that became a positive 37,620. Agreed on that so far? Okay, over here I distributed 500 times 4.18 times TF. And then I did 500 times 4.18 times negative 10, and I got that. Now I'm going to combine my like terms. So I add over 20900. And then I add over my 418 TF plus 418 TF. And then my final step would be to divide over that 2508. Sorry, I'm running out of room here, but I would divide over 2508, divide over 2508, and my temperature final comes out to be 23.3 degrees Celsius. Try this one on your own. So here we go. I'm going to put water on the left since that's what was given first. So 50 grams of water times 4.18, the specific heat, times final temperature minus 10. My iron is what's losing heat, right? It's going to cool down, so I go negative 50 times 0.45. Because the specific heat of iron was not the same as water. A lot of you use 4.18 on both sides. Okay, you have to make sure you're changing that. Then we go temperature final minus 90. Okay, so when I distribute that through, my numbers come out at 209 TF minus 2090 equals negative 22.5 TF plus 2025, right? These two negatives, when they multiply together, become a positive. I saw a couple people miss that also. So when I combine my like terms, that gives me 231.5 TF equals 4. And that gives me a temperature final of 17.78 degrees Celsius. Okay, so people that weren't quite there, do you see what the mistake was or what the catch was? Some people it was specific heat, some people forgot the negative, some people it was just an algebra thing. Okay, so there's several like places for error, so please just make sure you're being careful. Okay.